Hi, I'm Eva Murphy from Electronic Engineering at IT Sligo, and this is my Leaving Cert Maths Grinds channel. I'll regularly add new videos for both higher and ordinary level maths, so make sure you subscribe below and click the bell icon to be notified of new videos. Okay, so let's go on with another piece of theory. So the normal curve and the standard deviation. Okay. And so I'm down the bottom here, down here. Okay, so like we were saying, when you have a histogram and it's perfectly symmetrical, or even if it's not, you can draw a curve superimposed on top of it. Now, obviously on top of the data, I just drew it above it there so you could see what I'm doing. That curve represents the shape or the distribution of your histogram. Okay. Now, what's interesting is if you gather typical characteristics such as height, IQ, mass, failure rates, shoe size, anything like that, if you take enough samples, you will find that an awful lot of things can be fitted to a normal distribution curve. Okay, or a normal curve. Okay, which makes this curve extremely powerful. And it's probably why there's so much statistics developed around it. And it's because an awful lot of things in life fit what this normal distribution curve, also called a normal curve, also called the bell curve. Okay, right. In a normal bell curve, your mean is in the middle, okay? And you can take all of your data, or practically all of your data, 99.7% of your data, and you can split it up into standard deviations. And we generally have 3 standard deviations below the mean, and we have another 3 standard deviations above, okay? So you do maths, you basically take your min value and you take your mean, you get the difference between them and you divide by 3, or else you take your max value and your min value and you divide it by 6. Okay, and that's how you work out your standard deviation, the size of it. Okay, and we did a tiny bit of that when we did the 2014 question 7 in the last class, where we had to estimate our standard deviation size. Okay, so that's for any data. This standard deviations is what's called the empirical rule, and I'll come back to that again in a minute. Well, I won't, it's down here in the bottom, so let me do it now. So down here, okay, what you find is that if you are between 1 standard deviation of the mean, 68% of all of your data will lie between it. If you go between plus or minus 2 standard deviations around your mean, you'll find that 95% of your data will be under that. And if you go between plus and minus 3 standard deviations, you will find that 99.7% of your data will fall under that proportion of the curve. Okay, those percentages that I'm quoting, you have to know by heart. They're not written anywhere, they're not in any log tables. They are the empirical rule and you need to know them. Okay, and why is that? Well, as you can see, a histogram or a normal distribution curve, the highest frequency occurs in the center. Okay, so therefore, if you go left and right of the mean, and the mean is always that very central peak part, if you go left and right of the mean, you've got a huge proportion of people. Okay, and that's why 68% of it is between just plus or minus 1 standard deviation of the mean. Okay, widen it a little bit more, so take in 2 more bars, for example, and now you've got, or even 2.5. Now you've got 95% of the data. And then widen it that you go out another standard deviation. So from here all the way up to the top, you've got 99.7%. Okay. So really powerful that I can tell you that you can gather shoe sizes or marks in a test or people's height or anything like that. And I will know for certainty that 68% of you will have shoe sizes within 1 standard deviation of the mean. Okay, or that your marks in your Leaving Cert maths will be 68% of you will be plus or minus 1 standard deviation of the mean. Okay, so it's quite powerful that you can state these percentages about any data. So for example, let's just read this one. Suppose it takes you 30 minutes on average for your journey to school with a standard deviation of 4 minutes. Given that the distribution of these journey times is normal, okay, so it has to state that so that you can use the empirical rule. That is approximates the normal curve. Then using the empirical rule, find the percentage of journeys you will arrive at school taking less than 34 minutes. Okay, so you have to look at the mean, which is 30, and you have to look at the standard deviation. Okay, so 30 is bang on there in the center. You go up 1 standard deviation, okay, and you are at 34 minutes. Okay, so the percentage of journeys is as follows. Okay, so it's the easiest way to explain it. So between these two here is 68%, but you've also to take in this part here because it didn't say between 26 minutes, for example, which is down 1 standard deviation up to 44. It says less than 34. Okay, now I'll come back to it in a minute. More than 34 then is easy because it's 100% minus that. Less than 22 again is easy because again it's up to 22 minutes, but it's the more than 22 then that's a little bit harder. Okay, so this one has the graphs done for me. So how you do it is you break up the 68%, that's 1 standard deviation. Okay, you then divide 95 by 2, okay, and you get, I think it's 47.5. Yeah, so there's 47.5 between here and here, okay, but 34% of it is here already. So that's where they get the 13.5 here. Okay, that you then got to know that if you come out to 3 standard deviations, that's 99.7. You divide that by 2 and then you figure out what's here. So it takes a little bit of thinking to work out what's between the standard deviations. And I'm going to do an exam question. The third exam question that I do will be exactly on this, and I'll show you the maths behind it, okay? It's not overly difficult. It just takes a little bit of thinking about the first time you do it. Okay, so that's the empirical rule, and you've got to know it, okay? Because it's questions like this that they'll ask you. So for example, in a factory, if you're making handles for something, how many of them, and the typical width of, or the typical length of the handle is 10 centimeters with a 1% tolerance, how many of them will pass the test, okay? And it's this type of questions that you've got to know, I suppose, how to work the empirical rule. Where the empirical rule also comes into is hypothesis testing, Z-scores, and this 95% confidence interval, okay? It's this 95% confidence interval that's here as well. Okay, so that's the empirical rule. Okay, now, I also want to do normalization with you, so just let me find this. Okay. So in any normal distribution curve, your mean is in the middle, okay? And then you go up 3 standard deviations and you go down 3 standard deviations, okay? For the purposes of comparing scores, for comparing how well machines work, for comparing flooding in 2 different towns. You have to normalize your data for proper comparisons. So in other words, if I said something like the River Moy, goodness, the River Moy is at 3 meters deep today, and whereas the River Garavogue in Sligo, for example, is at 10 meters. And I ask you, which one is at risk of flooding? Okay. And I gave you the mean height. Okay. You can't really tell me which one is at risk of flooding, because you need to be able to compare those 2 values I gave you to the mean height of those rivers and the standard deviation. In other words, how much does it rise and fall by typically? Okay, so it is much better then where we move the mean, or in other words, normalize the mean, that it's sitting right on a 0 line on a normalized curve, and we go up in steps of standard deviations. Okay, so when you standardize, and this whole standardizing is what's called a Z-scores. So let me read here for a minute. When standardizing data into Z-scores, you subtract the mean of the data from every data value. And the end result of this is that the mean will shift to 0. Okay, and as we already know, such subtraction does not change the standard deviation. So in other words, if you subtract the same value of every data point, then your standard deviation, which is a measure of spread, it actually stays the same. Okay, you just shift the curve down. And we did this when we looked at that growth hormone exam question, where in that particular case, everything shifted up. Your mean changes, but your standard deviation doesn't. Okay, and then 2, we divide each of the shifted values by the standard deviation, and this shifts the standard deviation to 1. Okay, such division does not change the mean when the mean is 0. Okay, you don't have to know that's going on in the background, but you do have to know the overall result. Okay, so standardizing into Z-scores makes the mean 0 in the center. And it's 0 because it is 0 standard deviations away from the mean. It is the mean, okay? So it is centered on 0. Standardizing into Z-scores changes the spread by making the standard deviation a normalized step size of 1. So 1 standard deviation, 2 deviations, 3 deviations, okay? As compared to, in this particular case, where if you remember this one we were doing when we were arriving at school, standard deviation was 4 minutes, we went up in steps of 4. So this was 4, 8, 12, okay? On a different question, the standard deviation would be 10 and you'd be going up in steps of 10. Now you're not, you're going up in 1 standard deviation, whatever that standard deviation size is. Going up in 2 standard deviations, going up in 3. Okay, so going up in 1, you were writing for me, going up in 1, going up in 2, going up in 3. Okay, so that's what Z-scores, that's why we do Z-scores. We use them for comparisons, or comparing, I suppose, between different types of data to make a good comparison. So, and again, we don't have to do it, but I want to give you the type of question it's good for. So Bert and Ernie study maths in 2 separate classes with a large number of students in each class. I'm reading here in the example. The 2 groups sit at a different class test in maths. Both the tests are at a similar level, but are set and corrected by 2 different teachers of maths. Bert scored 90 and Ernie scored 80. When you look at that, first off, you think, oh, Bertie's result is better. But is it? Okay. You know, is that a true comparison? Was the test at the same level? Okay. Perhaps Ernie's test was harder. Perhaps Ernie's teacher marks much harder than Bert's teacher. Perhaps Bert's teacher gives attempt marks. Perhaps Ernie's teacher doesn't. So that's what I mean by it's not really a fair comparison when you're just looking at the percentages. So what you do is you compare them to, well, what did everybody get what was the mean in Bert's class versus what was the mean in Ernie's class. And then you look at the spread between the data. So in other words, standard deviation. What was the standard deviation in Bert's class versus the standard deviation in Ernie's class? Okay, and you do that using the standardizing formula, which is the z-score formula. Z is equal to x minus mu over theta. Okay, and what you'll end up seeing is that actually Ernie did better. Okay, when you normalize the data, Ernie actually did better. Okay, so it's examples of this I want to take you through in the next few exam questions, where we look at how do you standardize data and what does z-score values actually mean. Okay, and I'll take you into the log tables and we look at what, when you get a z-score and you look it up in the log tables, what does that mean? This is an example of one up here. That's your z-score tables. What do those values in the table actually mean and how do you read them? We look at two-tailed tests. This looks like it's a two-tailed test. We looked at one-tailed test, and we'll take it from there. Okay, and all the while then leading up to hypothesis testing, which we'll do in the next theory class. If you've enjoyed this video, then why not join us in IT Sligo and use maths in practice. In conjunction with industry, we've designed an exciting new program in electronics and self-driving technologies, which uses cutting-edge techniques such as artificial intelligence, computer vision, and virtual and augmented reality. You'll need a H5 in maths to qualify. Check out the link below.